Namaskar and welcome to CEC Gurukul lectures. I am Dr. Kumar Shantanu, Associate Professor of Botany from Deshbandhu College, University of Delhi. In this ongoing series of lectures on various topics of analytical techniques which are applied in plant sciences, we are currently going through various techniques involving microscopy. In microscopy, we have previously discussed the basic principles of microscopy. We have also understood the functioning of light microscopy, confocal microscopy, and various different types of phase contrast microscopes and other light microscopes. Today, we shall continue our journey of microscopy by moving ahead, and today we shall be discussing about electron microscopy. Now, before we hop on to the topic directly, I would like to recapitulate and introduce to our viewers to a very vital concept used in microscopy and which is called as numerical aperture. So, let us first try to understand what is a numerical aperture, because this concept of numerical aperture is very vital in understanding the basic degree of resolution and why we require different types of microscopes using different beam of electromagnets. So, the numerical aperture of the objective lens of a microscope, it is a measure of its resolving power. So, how it is calculated? The value of numerical aperture is given by the formula numerical aperture is equal to n sin alpha. Now, let us try to understand in brief about this formula. Here, when we talk about n sin alpha, n refers to the refractive index of the medium in which our object and the light would be traveling. And as far as alpha is concerned, it is the half the angle subtended by the rays entering into the objective lens. Now, this concept of alpha is very crucial. So, because of this particular formula of numerical aperture, we can say that if the numerical aperture is higher will be the resolving power, and similarly with lower numerical aperture, low resolving power will be resulted. So, let us try to understand this numerical aperture concept with the help of the diagram. So, here is our objective lens. Now, this objective lens, on this objective lens, the light will subtend in a angular manner. So, this is the angle in which the light will subtend over an objective lens. So, half of this entire angle of subtendent, it is called as theta, or sometimes it is also called as alpha. Sometimes we call it nu also. And since the medium here happens to be air, so the refractive index is 1 here. So, as this angle would keep on increasing, so if we move the objective lens closer to the object or closer to the stage of the microscope, this angle will keep on increasing. For example, you can see here in this diagram, the angle of theta angle is smaller as compared to when the objective lens has been brought closer, and if this objective lens has been brought further close, the value of theta has further increased. So, theoretically, we can increase the value of theta up to 90 degree. So applying that principle, sine 90 is 1. So the maximum value for sine alpha or sine theta could be 1, and the refractive index of the medium in which our objective lens is there, this will determine the value of numerical aperture. So if the objective lens is in the medium air, so the value will be 1 and the value of numerical aperture would be 1. And if the refractive index value is increasing by changing the medium, for example, if we apply oil in this area between objective and the focal plane, the refractive index of the oil happens to be 1.5 or 1.6. So the maximum value which can be attained, the maximum value of numerical aperture could be theoretically 1.5 or 1.6. So apart from that, there are only a small number of variables which affect the resolving power of a microscope. So as we have discussed, the refractive index can be increased by immersing the sample in oil. The oil can have can be of the refractive index 1.5 or 1.6, and we can also change the angle alpha or angle theta by moving the lens closer to the specimen. So the upper theoretical limit of alpha could be 90 degree, which means that the value of sine alpha cannot exceed 1. Hence, maximum numerical aperture of an optical system employing an oil immersion lens will be 1.5. So here, with the help of this diagram, you can very well see that by increasing the refractive index of various media, we can increase the numerical aperture to an extent. So when we apply water, the refractive index is merely 1.33. When we apply glycerine, it is 1.47. When we apply oil, it is 1.5, and when we apply a special oil, it is 1.66. So by increasing the immersion media, we can enhance numerical aperture to a particular extent. And as we have already discussed, that sine alpha could have a practical maximum value of 90 degree. So this value could be 1. So numerical aperture would greatly depend upon the immersion media which we are using. Between objective lens, here is your objective lens, and here is the plane of specimen, and between these the immersion media could be used. So as we have already talked about, that higher the numerical aperture, higher the resolution of any image would be. So let us try to understand what is a resolution. So a microscope which uses white light, it has an average wavelength of approximately 550 nanometer. So the resolving power of that microscope, which is using white light with an average wavelength of 550 nanometer, it will be approximately 550 upon 1.5. 1.5 the maximum value of numerical aperture. So it will be around 220 nanometer. So with the help of a microscope which is using white light, we can get a maximum resolution of 220 nanometer. This means that any object, that is any objects which are closer to one another or smaller than 200 or 220 nanometer cannot be distinguished. Now this particular concept of resolution can be understood with the help of this diagram, which says that the two objects, when we are unable to distinguish between two separate objects or smaller objects into two separate points, these are unresolved images. But with a higher resolution, we could start identifying them as two distinct points, and with a fully resolved image, these two points as compared to the previous image can be distinguished into two distinguished and two separate points. So that is the meaning of resolution. So any object which are placed together at a distance less than 200 or 220 nanometer cannot be theoretically distinguished with the help of a microscope which uses white light. So a resolving power of 220 nanometer is adequate enough to see some details of subcellular structures also. But many organelles such as ribosomes, cellular membranes, microtubules, microfilaments, intermediate filaments and chromatin fibers, these cannot be resolved at this level. So since the wavelength of an electron is much shorter than that of a visible light, and electron microscope has a theoretical limit of resolution much lower than that of the light microscope. So because of the limitation of resolution of a microscope which is using white light or visible light, we could change the wavelength of the source of light, and electron beams, they have a much shorter wavelength, and because of their shorter wavelength, an electron microscope could give us a better resolution. So electron microscope thus offers the possibility of increasing the resolving power multiple folds. So let us try to understand and compare various sizes of different day-to-day object and see that which observation instrument or tool would be sufficient enough to have a better visibility. So here is a scale on which different objects are placed. For example, here on the leftmost side, a child can have a length of approximately 1 meter. As we are moving towards right, the objects given as an illustration, they are shorter in length. So a child and a hand and a finger, and then moving towards the hair. So as we move towards right, the size of these objects are gradually becoming smaller. So a bacteria will have a dimension to the range of 1 micrometer only. Okay, and similarly a DNA molecule will have a dimension in a range of 10 nanometers, and an atom will have a range of merely 0.1 nanometer. So as we are moving towards right in this illustrative picture, we can say that these objects are gradually becoming smaller and smaller. And to observe these objects, the observational tools have to be changed. For example, since the size of object is in the range of 1 millimeter, it can be observed or they are visible through our naked eyes. But as any object keeps on becoming shorter, we have to use a light microscope. So the range of resolution of a light microscope is limited up to 100 to 200 nanometers only, and beyond this size, electron microscopes would be used to clearly distinguish two different points of an object, or to observe even the minutest of details of the objects. For example, viruses would always be observed in a much better way with the help of electron microscope. Similarly, the DNAs or the glucose molecules or even the atoms would be observed in terms of their dimension and structure with the help of a special microscope called as electron microscope. An electron microscope would use electron beams with a very low wavelength, or I could say very high frequency wavelengths. So they would be used as the source of rays. So let us talk about electron microscopes now. So the electrostatic and electromagnetic lenses are used in an electron microscope to control the electron beam and focus it to form an image. And there are two types of electron microscopes. Primarily, one is called as transmission electron microscope and the other one is called as scanning electron microscope. So here is a picture of a very retro model of electron microscope. It looks a very massive and very complicated because the entire functioning depends on multiple factors which we would be seeing in our lectures to come. And also, if you could observe that it requires a great many preparation to just install, and the size also happens to be very huge. And this model has become refined over the period of time, but the basic principle of functioning of a electron microscope has remained the same. So let us talk about transmission electron microscope and scanning electron microscope. In transmission electron microscope, also termed as TEM, the electrons are transmitted through an object and then they are focused by the lenses to form the image. Contrary to TEM or transmission electron microscope, in case of scanning electron microscope, the electrons are reflected by the object in a scanned pattern which are then used to form the image. So here there is a comparative diagram of two different types of electron microscope. On the left is scanning electron microscope, whereas on the right hand side you could observe a transmission electron microscope. In case of transmission electron microscope, you could see that the sample or the specimen has been placed in the midway of the path of electron beams. So from an electron gun or from a source from where electron rays are bombarded or generated or emitted, it is these electron beams, they pass through some of the lenses. We will talk about the nature of these lenses, but for now we will call them lenses only. So they pass through some of the specialized lenses and then they also pass through the sample, and these samples, they deflect and divert these electron beams, and these deflected and diverted electron beams, then they pass through multiple different sets of lenses and then an image would be created on a sensitive plate. Now let us see the basic principle with the help of an schematic diagram of scanning electron microscope. In scanning electron microscope, the electron beams are emitted from an electron gun, or you could say the source of electron beam. They pass through multiple set of lenses. The function of these lenses is to streamline these electron beams towards the direction of objective, and here the objective is placed at the end, and from this objective the electron beams, they fall off and then they are reflected back on the opposite direction. Now these reflected electron beams, they are reflected as per the contortions or the profile of the surface of the object which is placed here, and these deflected or reflected electron beams, they are detected with the help of some sensory instruments, and these sensory instruments, then they perceive and then they create a computer generated image of the surface. So that's the basic difference between the transmission electron microscope, where the electron beams, they actually pass through the object, whereas in case of scanning electron microscope, the electron beams are basically deflected from the surface of the specimen. Now let us talk about the basic components of an electron microscope. As we have already seen the basic picture of a electron microscope, we have also observed that it's huge in size and it contains different components. So the entire electron microscope could be divided into 5 basic components. The first component happens to be the vacuum system. The second one is the electron gun. Third one is electromagnetic lenses and image formation. The fourth is the photographic system, and fifth, the cooling system. So we shall talk about these 5 basic components of electron microscope, and then we shall further move to study and discuss transmission electron microscope in detail, and also different methods used for the preparation of material for electron microscope in our next lecture. Thank you so much for your patient listening.